Thank you, Marty. And thanks, Professor Moss, for agreeing to give this presentation. So I would like to introduce Professor Rob Moss, who just came back from reconnaissance, the advanced team reconnaissance from Turkey. And Professor Moss has been teaching at San Luis Obispo, in Cal Poly, San Luis Obispo, for over 16 years. In areas of his areas of expertise include geotechnical earthquake engineering, engineering seismology, and risk and reliability with respect to earthquake engineering. And I know for sure that he is an expert on geomorphology too. Rob earned his PhD from UC Berkeley with his research into probabilistic liquefaction triggering. As we know that Moss et al. Is a well-known triggering relationship when we use CPTs for liquefaction triggering. And his minors are in engineering seismology and structural reliability. He's been a member of 9 earthquake reconnaissance teams traveling to Turkey, Nepal, Japan, Chile, Alaska, Turkey, India, Mexico, and around California. So just a little background where it started. 3 weeks ago, we had a research workshop at RDEC for seismic and flood-related research ideas. We invited a few academic professors and industry experts. And Professor Moss was supposed to be in that workshop, but he decided to go to Turkey as a member of the advanced reconnaissance team after this earthquake. And the reason is simple, that many of the observations that you see after an earthquake, those may not be there for a longer period. So seeing those, making observations and taking notes of those is extremely valuable for our state of practice. And Professor Moss is an expert on this, and we are glad that he will be able to share some of his observations with us today. With that, I will be out of the way. Professor Moss, it's all yours. Thank you.
Thanks,
Khaled, before Professor Moss starts, I'm getting notification that some people have no audio. If you have no audio, turn it off and turn it back on. WebEx is acting up today. If not, have it call you through your phone, not through your computer. Over to you, Dr. Moss. Thank you.
Thanks, Khaled. Thanks, Marty. And we are recording this, so if there are some technical difficulties, you can look at it later. Okay, so let's get started so that we can get through some of this stuff. As Khaled said, I just got back from Turkey, a part of GEER, and this was a joint effort between GEER and METU. I work closely with my colleague, Professor Ander Chetan in METU, and I have for a couple decades now. And when this event came up, I knew that I needed to jump in and go help out. And so I'm going to give you the preliminary briefing because I was on the advanced team. We have Team A that's over there right now doing some more granular digging on collecting data, and we'll probably be sending subsequent teams. And all this is sponsored by NSF and NEHRP. So I'm gonna give you the big picture, and then we'll get to, I know what you want to look at is the embankment dams, but we need to set the stage first. So my role in events like this is to get in early and do the big picture stuff. And when I say get in early, that means we get in after primary rescue, so usually within a week to 2 weeks from the event, so that we're not impeding the rescue, but before reconstruction starts, which is usually about a month in. And we try to acquire perishable data so that we can learn the most from these events, so that it's not just, oh, there's another event, there's another event. We're trying to acquire the data, learn from it, and move forward. And one of the objectives of GEER is to disseminate this information widely, like this talk here, to people who are interested and need this information. As Khaled mentioned, I've done this a lot. my expertise lies in getting into difficult and hard places and figuring out what needs to be done and what information needs to be acquired. Our event, so tectonically, the Anatolian block is kind of this pipseed where it's getting squeezed between several plates. There's a triple junction there, and that's why Turkey's such a hotspot for seismicity. Usually you hear discussions about the Northern Anatolian Fault because it runs right past Istanbul. Here we're on the Eastern Anatolian Fault that runs through a breadbasket area and the border with Syria. And we had, we're calling it events because it was really a series of events. The 7-8 actually started on a fault that was not the Eastern Anatolian Fault, and then it jumped onto the Eastern Anatolian Fault, and we had bidirectional rupture. And then there was a 7-5 on a separate fault up north, and that was actually two faults, the Suru and the Comic faults, and that was a bidirectional rupture as well. And then there was a bunch of aftershocks, and here I'm showing some aftershock sequences. And the beach ball in the lower right is showing that these are all left lateral. So these are all left lateral events. This, I'm not going to show the animation from this, but this gives us an image of what I was talking about, where we have bidirectional rupture on the Eastern Anatolian, and then we have bidirectional rupture on the Surgu chemic faults. And when I say bidirectional, that means that it's centered in the middle and then it's propagating out to the ends. And what that means from a ground shaking perspective is that we have seen evidence of some directivity, particularly in the south, and that directionality leads to that directivity. So imprinting this on a fault map, these are all mapped faults. And here we had the initiation, which was off of the East Anatolian. We had the East Anatolian rupturing north and south. And then to the north, 9 hours later, we had the Surgu and Chemic faults rupture together. This map I found particularly interesting because it has showing cities, it shows the faulting, it shows the epicenters, and it shows some topography and some geomorphology. And, you know, why are all the cities lined up on the fault? Well, the fault's there, and then the gouging of the fault makes it easily erodible, and so we have rivers there, and then people move into the river valleys, and you have agriculture, and so that's why we have this imprinting of faulting and river systems and dams and people and agriculture all right along the fault. And of course, that's where the strongest ground shaking was as well. This image shows some displacement estimates, and what, you know, from the big picture, we're seeing upwards of 4 meters of left lateral strike slip displacement, and there were incidences of displacement up to 7 meters in particular locations. So lots of fault rupture through developed regions, through infrastructure, right in the middle of it. Here I'm showing the faults, and I'm showing the strong motion stations. So one of the upshots of this event is that it's very well recorded. And right at this moment, we're in the process of vetting all the strong ground motions and vetting the stations and figuring out what looks reasonable and what we need to investigate so that we have the characterization of the loading pinned down as best as we can, because we can make all the observations of ground damage and geotechnical related issues, and if we don't have strong ground shaking, then it's not very useful for us. For this event, we've got all the observations of stuff falling down and ripping apart, and we have the loading that's going to go along with it. So I think we're going to get a lot of useful information out of this event. Just to reference you, I'm going to be mentioning some names. So this town of Golbashi was just north of the epicenter for the main event. You've probably seen lots of pictures from the town of Marash, which was essentially leveled. Pazarchik is just south of the epicenter. Lots of fault rupture around there. Elbistan is to the north off of the northern ruptures. Iskenderun is over in the port area, and there's lots of port facilities that we visited, and there was lots of liquefaction and ground damage over there. You've seen lots of news from Antakya. Antakya also was essentially leveled. And note that Antakya is also the ancient city of Antioch. And, there's a long history of civilization and a long history of earthquakes destroying cities. And what we're trying to do is do better. We want to do better than what's been done for the last couple of millennia where we just rebuild. And then this town of Antep, which ended up being our headquarters for all of our initial investigations. So the advanced team was me and Ozgor Kozaki. We were in country, and then we embedded with Andr Chetin's researchers, and we got on the ground and we covered as much ground as possible to try to put our arms around the problem. Usually with these events, we try to get in the air and get the big picture, but the airspace was restricted by the military, and so we were not able to get in the air. And so lots and lots of driving. And this was our coverage as of the time that we pulled out, which means that we covered top to bottom and side to side. And that's what the advanced team is supposed to do. Team A that's near there right now, they're focusing in on particular areas where we need to collect more granular data. A little bit about the motions. It was a 1-2 punch. There was the 7-8, and then there was the 7-5. And here I'm showing some ground shaking near the epicenter. This was from a preliminary report that came out of Metu. And then I'm showing ground motions south of the epicenter. And what you can notice right away is that there was a lot of long period motion. So for the image on the left, at a 1 second period, we see spectral accelerations greater than 1g. And on the right, again, 1 second period, and we see spectral accelerations on the order of 2g. So a lot of demand. There was a lot, very intense ground shaking. Depending on where you were, sometimes the main event felt like 3 events. And then the second event came along. And so if it was a structure that had been, pushed past its elastic point, then the second event came along and pushed it over. So what we see is a lot of damage. And you guys have seen the images. The structural response is just, it's almost hopeless. Everything that you could ever imagine that has happened to structures happened here. On any given block, and you're walking through these cities, you can see everything. We have soft story collapse. We have poorly reinforced structures. We have structures that are reinforced well, but then they didn't do the foundations. It's overwhelming how much structural damage there is. And you can see that in the death toll. The picture on the left shows Marash, or no, sorry, that's Antakya, almost completely leveled. On the right, you can see varying structural performance and foundation performance, from foundation punching to soft story to buildings that did well to buildings that are just complete piles of rubble. And we saw this over and over and over again. And our colleagues at ERI, there was a small advanced team that joined us, and their goal was to march through the city, the various cities, and document this. And so we're talking about 10 to 12 cities where this was over and over again, the type of images that you see. Again, total collapse. And I'll talk about it at the end, but this has to do with not that the building codes are bad, it has to do with no enforcement of the building codes. Okay, so then getting on to surface fault rupture, it was everywhere. I visited a lot of events, and this one, it's just, there's so much surface fault rupture, and every textbook type of example of surface fault rupture you can think of is here. There's horsetails and flowers and stepovers and an echelon, and it's like everywhere. And it's so dramatic, and it ruptured through buildings, and it ruptured through infrastructure, and it ruptured through tunnels and highways, and on and on and on. It's just hundreds and hundreds of kilometers of surface fault rupture. On the left, I'm showing some sag ponds that opened up and structure that was hammered. On the right, you're seeing, these great markers. We have fences that give us great markers for this fault offset. Rupturing through fields, rupturing through hills, rupturing through towns. So dramatic. And I've been, the last 3.5 years, I've been working on the fault displacement hazard initiative, where we're developing new PFDHA models. And boy, this event is going to feed a lot of data into our PFDHA models. Liquefaction was widespread. Anywhere it could have liquefied, it did. On the left, I would hire those structural engineers any day. They didn't do any geotech on this building. On the right, we're seeing port facilities with massive venting of liquefied material. Again, port facilities, you can see that the pile-supported wharfs did great, and everything else that was on fill, not so great. On the right, lateral spreading, cutting through towns and buildings. Huge lateral spreads at point bars. Liquefaction and foundation punching. In the middle figure, you can see the tilt to the building because the structure's fine, but the liquefied material gave us the punching and differential settlement. Sand boils, this was at a bend in the highway where the fault ruptured through, and then also there was a creek, and the whole embankment liquefied, and the road essentially blew up. More port liquefaction, lots of port damage due to this. And this one on the right, there was a gravel boil there. We actually found one place where there was boil ejecta, and it was freshwater shells. So apparently this old stream channel had a bunch of freshwater shells in it, and then had been buried and liquefied, and then we had shell ejecta. Never seen that before. Again, more port damage, liquefaction. Several towns had huge swaths of liquefaction that compounded the damage from the ground shaking. Okay, now here's the juicy stuff that you're all waiting for: embankment dams. So I was tasked with visiting 5 embankment dams, and so with Professor Chetnut Metu, we're working with the dam agency there, and they reached out and they said, please visit these dams and provide us feedback. So I've got pinpoints showing the dams. The black lines are showing the surface fault rupture, and the green dots are showing the strong motion stations. And I want to juxtapose this with, I also worked on the India earthquake, the Bhuj earthquake, and there we had widespread damage to embankment dams, but we had no ground motions. There was one ground motion station in the town of, oh gosh, I'm forgetting the name of the town. It'll come to me. And it was in the basement of a building, and it wasn't bolted down. And so we have a record of the strong motion station walking across the basement and then the building falling on it. So we had no ground motion estimates. With this one, we are going to have really good ground motion estimates to then correlate to the ground damage that we're seeing, or the embankment damage. The first one that we visited was the Sultan Suyu Dam. This one, so let's see, most of the dams, and I have the specific ages written down, most of the dams were built between the late 80s and early 90s, except for this was an older dam, and I believe, I'll have to check my notes, but I think this one was built in the late 50s, early 60s. And initially what we see is large crest cracking, and we see some vertical and lateral deformation of the crest. So that's the picture on the right. The picture on the left, I'm down on the face, and we see large faced cracking. And what I'm circling there is the same structure to give you some reference. And this was the first dam I visited, and what shocked me is how similar this is to the earth dams that we visited in India and the deformation patterns. We see crest cracking and deformation. We see face cracking. And then I get down to the toe, and the left image, you see the toe actually translated out. And then walking around, I find ground cracks at the toe and I find sand boils. The outlet structures were fine. Note that Turkey is undergoing a drought right now. I don't know what the pool was before the earthquake, but I know that the dam agency did a quick assessment, and anywhere there was cracking observed at the dams, they drew it down. And so when we got there, this was drawn down to low pool. All the outlet structures were functioning. This one, the outlet structures were fine, but the dam had experienced significant cracking and deformation, and liquefaction is the culprit here. We took samples of this, and we're testing these samples back at the lab in Metu, but this one was a fine sand, and we found sand boils all around the toe. So liquefaction is the culprit here. The next one we visited, this was, for some reason, they have, and I haven't figured it out, they have terminology where they call some embankment dams dams and some ponds. This one's what's called a pond for some reason. I think it has to do with the use. And we see pretty large crest cracking on the left. We see large scarps on the face. So this is the upstream face on the right. And then we get down to the toe and we find sand boils. Both of these dams, the height of the embankment ranges anywhere from about 50 to 60 meters. One of the nice things is most dams, they have these great signs that are posted right there that have all the specific data on it. So this one was, mid 90s, and they give you the, the area of the reservoir and the elevations. And so great data on that. Also, because we're working with the dam agencies, we're getting as many as-builts and all the specs that they have on it. So we're going to have really good case histories. Again, we took samples, sent them back to the lab, doing testing on that. Liquefaction. Here's another dam, Yarsli Dam. Outlet structure was fine. Minor crest cracking. You can see in the picture on the right, there was a little bit of tilt to the parapet wall. Crest, so these longitudinal cracks, not very deep. The faces were fine, both upstream and downstream faces fine. The outlet structure is fine. This one appears to just be seismic compression. Pretty easy fix. There was no transverse cracks, just these longitudinal cracks in the upper fill material on the crest. Here's an interesting dam. This had rock abutments on either side. Again, crest cracking. There was a little bit of superficial cracking in the outlet structure, not in the structure itself, but in the concrete apron in the middle picture. The ground shaking was pretty strong, as evidenced by, they used to have a little structure here on the crest of the dam, and it's demolished. And then on the left picture here, you can see there was lots and lots of rock fall, which usually coincides with high intensity ground shaking. So here we're standing back, picture on the right, and we're looking at the rock abutments. And if you can see, there's a dark line that runs across the face of the dam and then runs continuing the rock. That's the bathtub ring. And if you look closely, you can see a little bit of a sway back in this. And so again, this one appears to be seismic compression. The face, both faces, upstream, downstream faces looked fine. Outlet structure appeared to work fine. No other issues other than that crest cracking. And then we visited this Sugu Dam. Oh yeah, this is the old one. Yeah, I said the Sultan Suyu Dam was the oldest, but no, this is the old one. The Sultan Suyu Dam was circa 80s, and this one was late 50s. Older construction techniques. We get there and we see crest cracking, and it's nice they had that white stripe painted on the road, so we see lateral deformations. So longitudinal crest cracking, some lateral deformations, and it's really hard to see in this picture, but when I was there, it was evident that on the face there was some bulging, and the bulging coincided everywhere that there was some crest cracking. And so my thinking here is that this is older construction technique. It's unclear what materials they used or how well compacted it is, but it appears to be that there was some seismic slope stability that resulted in the longitudinal crest cracking, where then we had some vertical component where it dropped down, and then we see some coincident bulging on the upstream face of this dam. Again, these are all drawn down to low pool, where while they're doing damage assessment and figuring out how much reconstruction they need to move forward. They're moving fast because, as I said, they're in a drought and they need this water for agriculture. And so they're trying to do triage and figure out what they need to do to get these dams back online. Those are the 5 dams I visited. My colleagues at Metu, I think, visited at least 1 or 2 more since I left. And we will compile all that information in our first GEER report that is going to be coming out by April 6th. A couple other things to show you. Maybe you saw this in the press. This was kind of like splashed all over the news. After all the death and destruction, it's kind of nice to do something where nobody was hurt and there isn't like critical infrastructure issues. So we had a couple hours towards the end of one day and we visited this spot. And let's see. Yeah, so this is going to play. It's rather dramatic slide. There was a lot of conjecture about what was going on here. Somebody said, oh, it's fault rupture. Other people said, oh, it's karstic terrain. And but you can see that lots of deformations, but also I want you to look in the background here and see that the terrain is very hummocky with these deep channels. And when I go on these events, I talk to every local I can about their experiences. One, so I can empathize with their experience and humanize it, as opposed to dealing with, dealing with 50,000 people died. Here I talk to an individual and say, what was your experience? And say, oh, I lost, my cousins and this and that, and my house was destroyed, but, I have to go on living. And so there's that. And then you get really useful information. And what we found is that this town, the ancient name directly translates to village of big cracks. So there's, and Turkey's fantastic in that way. The towns have these names, and my geologist friends say that you don't need a geology map because you just ask them what the town name is, and the town name will be like, this is the hotel that got ripped apart by an earthquake, or this is the landslide town, or this is the limestone town, or this is the town that has, coal. And so here, this town was called Village of the Big Cracks, which was telling in and of itself. And then I climbed down, and you can see these dipping beds. These are dipping at about 8 to 10 degrees. The slope dips at about 10 to 20 degrees. It gets steep down at the toe. It's a formation that has some clay stones, and I got down to the bottom of the slide plane right at the head scarp, and I found this clay stone that had weathered and was remolded. And it turns out that it had rained a couple days pretty hard before the earthquake, and then the earthquake happened, and it seems to add up. I did some quick back of the envelope calculations, and we find that static factor safety on the order of 1.25 to 1.5, but very low KY. So you have a wetted a wetted clay stone, and then you give it a seismic kick, and then it remolds, and then you have this retrogressive failure moving up from the toe. So that was kind of a nice gee whiz type thing to dig into. Okay, so you know, from my perspective, trying to put my arms around this event, and one thing that I didn't touch on is that we were able to move throughout the damaged region quite easily within a week and a half of the event because the transportation infrastructure in Turkey performed brilliantly. It was amazing. The roads, the bridges, the huge viaducts, the tunnels with fault rupture through it, their transportation infrastructure is top notch. It was shocking how good it was compared to the commercial building stock. It was like night and day. We saw widespread liquefaction, and we can compare this directly to Adapazari. And Adapazari was, a large town or large city that was impacted by liquefaction, very similar to what we see here. But here we have on the order of 10 cities. So this is 10 times Adapazari when we're looking at liquefaction, building stock, and structural performance. Fault rupture everywhere. Fault rupturing through highways and buildings and pipelines, and we're trying to organize subsequent investigations of that because this response of lifelines to fault rupture is very useful information. One thing that was shocking was that we saw coincident fault rupture and liquefaction. Golbashi is a town like that where the fault ripped right through there, did an echelon stepping right through the town, and then you had liquefaction imprinted on top of that. So fault rupturing through liquefaction and lateral spreading all in this built environment. There's going to be a lot of work with the strong ground motions that is going to take a while. We're just scratching that, but there was a lot of long duration or long period stuff. There was a lot of directivity. We're going to have near fault measurements, and then we're going to have all this loading to use to correlate to how it impacts our built environment. The big heartbreaking aspect of this, and my heart goes out to all my Turkish colleagues and the whole country, is that this unfortunately was a man-made disaster. If they had followed their own building codes, the life loss would be an order of magnitude less. When I was there, I was comparing it. I worked the Chile event, 2010 Chile event, and the damage zone in Chile was huge. It was a subduction event, and so we're covering, hundreds of kilometers, and the damage zone here is similar in its scale. North to south, 400 kilometers or 500 kilometers, east to west, a couple hundred kilometers. So that the damage zone is the same size. And in Chile, we had on the order of hundreds of deaths because there they adhered to building codes. And here we have on the order of, 50,000 deaths because they're just not following the building codes. And then, of course, what you guys are most interested in is the embankment dams that provided what I think is useful lessons. We had varied performance. So we had some that experienced liquefaction and large stability issues, and those are going to have to be rebuilt extensively. Some that experienced just a little bit of seismic compression, and some in the middle. And with the ground shaking and collecting further case histories, I think we're going to have a wealth of data to use in our forecasting models moving forward. As I said, we've got another team over there right now doing detailed fault rupture mapping. We're trying to get some more work on the infrastructure. The trick is there that you need connections with the agencies to be able to access the gas lines and the water lines and the electrical transmission lines. So that's something that's being negotiated right now. Our Team A is doing detailed liquefaction mapping with Professor Chetin's team, and this is going to go on for months. Just like Adapazari, there needs to be block by block assessment of how liquefaction impacted the performance of the building stock. And then vetting the ground motions and the strong ground motion stations and coming up with the subsurface conditions there. So we understand fully how we go from source to site to what the response was that we saw. On the lower right was the advanced team. So me and Oz in the diagonals, and then Erhan, who is a professor locally in the left corner, and then Umut. And Umut is, he was already I advise doctoral students at Metu. He was already a doctoral student of mine, but now he's the country's foremost seismic dam expert after visiting, I think he's visited 7 dams now. And then the left picture shows me and Professor Chetan. And again, a lot of the motivation here was that as we continue to work together, I could go help him out because he's in the eye of the storm right now, doing the technical work and also dealing with the agencies. He's dedicated 2 days a week indefinitely to doing field reconnaissance with his team. And he is, as we're working closely, GEER and Metu, on trying to learn lessons from this event. So that is the end of my slideshow, and I am happy to field any and all questions.
Okay, thank you so much, Dr. Moss. This has been amazing, an amazing presentation. I have been copying the comments and the questions. I'm going to unmute everybody. I would appreciate if everybody would mute themselves. This way I can begin asking the individuals in order to respond to the questions and comments. The first person is Andy Farhan. Andy, I believe you're from our Fort Worth district, and you had a comment. You said you see one area, similar types of buildings, some collapse, some still there. Is it a foundation problem or just compliance with building code structural requirements? Just a first impression at this.
Yeah, all of the
Dr.
above. So yeah, so all of the above. What we have learned is that not only is there no adherence to building codes or ways to skip around the building codes, but that there are for the soils reports, that there are many situations where they just fabricate the soils report. You can actually pay a company and it'll make up a boring log and submit that as part of whatever your package is. And so we saw really poorly designed structures that fell down due to ground shaking. We saw well-designed structures that fell down due to the foundation failure. And then we saw a combination of the two: bad structures, bad foundations, and you end up with this pile of rubble. And then, you would be walking through and you would find where the building was well built. They did a good job on the foundation and it survived. And, we do that time and time again. This is not a hard thing. Their building codes are the same as our building codes, and we enforce it here. And in other countries, I've seen it enforced, like Chile. And then there are countries where there isn't enforcement, like Nepal and Turkey, and that's where you get the life loss. So it's a combination of all the above. We can design for liquefaction, we can design for fault rupture, we can design for all that stuff, and it's just either enforcing it or having the will to do that.
Okay, thank you. My next question is from Keith Kelson. He said it would be good for this audience to understand the process and criteria used to decide where to go first. Where are the most critical transient data? What can we learn now before the data goes away?
Well, I mean, that was the job of the advanced team, was to figure out what is most critical to collect right now. And what we're targeting the surface fault rupture, and we're trying to get some airborne imagery to do structure for motion. And we're trying to do that in the next week. We were shooting for LiDAR, but it looks like the structure for motion is going to happen immediately. And so we're going to go with the bird in the hand. The other is documenting the damage patterns due to liquefaction, because they're starting to bulldoze and scrape that up. So we're getting that information. And then also with the dams, getting images of what the deformations look like before they bulldoze the crest and start doing some type of rebuilding. And so that one dam, the Yarsalik Dam, by the time that was the one with the rock abutments, by the time we got there, they had to regrade it because that was an access road to villages that were on the other side. So we had acquired pictures from the dam manager of what the cracks actually looked like. And so that stuff goes away really quick. Yeah, I think that hits it for the urgent stuff. Thanks, Keith.
Okay. Go ahead, Doctor. Okay, I'm going to jump around a bit. I'm going to take the question that came in from Ben Mason at USGS. Any plans to fly drones over the dams, if allowed, to create DEM assets and track the earthquake-induced displacements? Any other site investigations planned? Surface wave testing, CPT?
Yes, yes, yes. Right now we have some drone operators that are from Metu that are embedded with Team A, and they're flying lots of stuff. And flying the dams is one of the tasks that we're set up to do. Of course, that's with the agreement with the dam agencies. Because of the chaos that ensued after the event, when we showed up to dams, even though we had permission from the dam agency to collect data, they had soldiers assigned to each dam. And so every time we would show up, we would show them our official letters and they would report it in. And we would move quickly and collect all the data that we needed before the Jefe showed up. And then they'd say, "Oh, I'm just doing my job." And we'd say, "Well, you know, the dam agency asked us to be here." And they say, "Well, I'm on the military side and we have to ask you to leave." So there's a lot of negotiating access. Um, the tensions are easing, and so there seems to be more agreement between what the military intent is and the dam agency's intent is. And I'm hoping that within the next few weeks, we'll have all the damaged dams flown with drone.
Okay, I'm going to do one more question and then we will stop at that point. As I mentioned earlier, I have compiled all the questions and I will send them to you for your response and comment. The last question is from Jeff Muncie with the Tennessee Valley Authority Dam Safety. The liquefaction observed at the base of some of the embankment dams, was it on the downstream or upstream side?
These are all on the upstream side.
Okay, thank you very much. At this point, I'm going to go ahead and end the presentation. As I stated, everybody's questions have been compiled and will be sent to Dr. Moss for his answers. Khaled, before we hang up, do you have any further comments?
Marty, I think we went quite fast. I would say that we still have a little bit time, so many people may have time. We have about 15 more minutes if we want to take advantage of Professor Moss being here. So,
okay, then how about we do this? I know people, you know, were having to sign off early because of, you know, other commitments and so forth. So I didn't want people to miss everything. But let's go ahead and ask. Well, I see him, Robin Charlwood. I believe you had a question. Why don't you go ahead and ask it?
Hi, thanks. So I was chairman of the ICOLD Committee on Concrete Dams, and I wondered if you have any quick comments on the concrete dams and also on the intake structures, which I got the impression performed very well.
I did not observe any concrete dams. I don't know what their inventory is, embankment dams versus concrete dams. That'll be information that we'll get forthcoming in the following weeks. But yeah, we were surprised at how well all the outlet structures and intake structures performed. The cracking, if we did see cracking, was completely superficial. Now, we weren't there and we weren't able to ask the dam operators if they were able to operate the gates. Although on one dam, we asked them and they said yes, but there was no pool to check if there was any leakages. But they said, yeah, the mechanism worked fine. but observationally, all those concrete structures performed quite well.
Well, I mean, which is really interesting because when Martin Whelan and I went to China, I mean, there the intake structures were just blitzed and it was really critical.
That was from Wenchuan?
Yes.
Yeah, interesting. Yeah, it has something to do with the ground motion characteristics.
Anyway, fantastic presentation. Thank you so much.
Thanks, Robin. Good question.
Okay, our next question is going to come from Todd Lohr. He's a member of the Corps of Engineers Risk Management Center located in Lakewood, Colorado. Todd, you should be unmuted. Go ahead and ask your question.
Oh, gee, I kind of wasn't ready for that. I just posed an inquiry regarding the measurement of deformations on these structures and maybe even away from the embankments themselves. But I saw a presentation recently from the Army Corps folks who've been monitoring Mosul Dam during the repairs that are occurring there, and they've been able to detect really small scale deformations and undulations in the surface over close periods of time using INSAR. My understanding is it can be challenging to use INSAR, but that might be a good application over a widespread area where you know it's tough to get drones in, or there's some access issues, because you can kind of back tag the satellite data and use it moving forward.
Yeah, I mean, that would be great if like if anybody on the call can have access to somebody that can start that ball rolling, then let's do it. I agree. INSAR is great. We can relatively easily do structure for motion, but then we're starting with whatever, you know, we're flying now. And the INSAR, like you said, we can back up to some point in time and pull those old sat images. So yes, I'm all for that.
Yeah, good.
Okay,
Bill
thank
Empson
you, Dr.
is
Moss. We have
pretty
another
expert.
question from Susan Henderson from the United States Bureau of Reclamation. Susan, I'm going to unmute you right now. Okay, you should be unmuted.
Good morning. I was just curious, I'm an emergency manager from the Pacific Northwest, and we're really concerned about Cascadia subduction zone events up here, followed by dam failures. So I was just curious, in your tour, were you given any opportunity or overheard conversations about how, when they were lowering these reservoirs, I would assume at a very high amount to try and lower them as fast as possible, what you heard emergency management-wise? Did they make notifications downstream? Did they even worry about what was going on downstream of these facilities, considering I'm sure there were a lot of rescue attempts going on? I was just curious about that balance. Thank you.
Yeah, no, great question. I think as our investigations evolve, we'll have some more information on what that looked like in the moment. All we had was information that there were damaged dams and that they had drawn them down if they needed to. And again, this was during a fairly prolonged drought, so it's unclear how much pool needed to be released. When we looked downstream, there was no evidence that there was a rapid drawdown, so there was no erosions in the channels, and there was no reports of any flooding downstream. All these dams that we looked at are agricultural, and so there is villages and towns that are downstream that would be in harm's way, but there was no evidence that there was any flooding issues. But I agree with you that sequence of earthquake, damage, trying to mitigate the hazard but not cause another hazard is a tricky one. And so hopefully we'll get some more sequenced information from the dam agencies as we move forward.
Thank you. I guess there are some benefits to a drought. Thank you.
Yeah, right.
Dr. Moss, our next question is from Zia Zafir with Kleinfelder in Sacramento, California. I will be unmuting them now.
Hi, Rob. This is Zia.
Hey.
So you mentioned that if the buildings were designed based on the code, that will be one order of less deaths. But I saw the ground motions were much higher than even the code right now. So what is your take on that? Do you think it's still there will be less damage because the ground motions were is still too high from the even the code what you had? And
The ground
also
motions, yeah. I mean, it's, you know, at this point it's conjecture, but the ground motions were high, but it was in the longer period range, and you wouldn't see all this collapse. I mean, you might see that the structures were non-salvageable, but you would see life safety performance out of the structures. And so, yeah, I think that even though the ground motions were high, I think that still that's going to hold true.
thanks.
Zia, so please post your question in the chat so I can make sure I include that with everybody else.
I'm doing that, Ken.
Thank you. Our next question is coming from Andy Hill. Andy, let me unmute you.
Hey guys, can you hear me?
I can hear you.
Yeah, hey,
Okay.
Thanks for the great presentation. Really, really interesting. And this question is really kind of about some facts you may not have access to just yet. So it's really about the performance you noted with regard to the outlet structures and how they were still able to, you know, drain these reservoirs and looked pretty good for the most part, but you saw a lot of distress in the actual embankments themselves. Do you have any idea if that had to do anything with anything that was done during construction, like densifying these potential liquefiable layers under these outlet structures, or, you know, any other treatments that may have been done versus what's been done in the embankments? Any kind of just general observations or knowledge about how the difference in performance between those two pieces came out? Or
Yeah,
was it
it's a great question. I mean, I'm gonna go on a limb and say that probably nobody addressed liquefaction when they built any of these dams. And I mean that just kind of it's par for the course, right? We have a river and the river's there because the fault's there and the river deposits sand, and then we built the dams prior to fully understanding things, and now we have issues with dams on faults and liquefiable material. So unless they're going to come out with some as-built and say, yeah, we recognize this and we dealt with it. The rock abutment dam, that was clearly a rock channel outlet, and so I don't think that there was any liquefiable material that could be there. But all the other dams, probably whether liquefied or not, is just a function of the ground shaking, and that's going to be determined as we get further into this analysis. But in terms of the construction details, how well the dams were built, I think we're going to be looking at the older generation dams. So those were the 50s, 60s versus the younger generation dams, which are the 80s, 90s. And I'm going to be really interested to see what their best practices are in terms of how they built them then versus how they built them now. But that's to be determined. So more to come, Andy.
Thank you, sir. Very interesting.
Okay, let's see. Our next question will be coming from, we have so many, it's hard to select one. How about Natalie Ehrlich? I believe she is still on. Natalie, if you would unmute yourself. Going to make sure you're unmuted. Give me 1 second. I believe Natalie has dropped off. Okay, the next question. I hope I'm pronouncing your name right. Onur Tazdan.
Yes, you said my name correctly. I'm with Geosyntec. I put the question there, but the question is mostly there's, I believe, more than 100 dams in the region that is subjected to this high ground motion. Are they also inspecting the dams that have not experienced large deformations so that we can draw lessons on what worked and what design types or dam types worked better for this event? Thank you.
Yep. great question. I totally agree with you, right? We need the damaged ones and the undamaged ones. Right now, they're still doing triage, but as you know, the undamaged ones, they're not going to go away. And so as we move forward and we have more time, we can go through and compare ground shaking and if there's any, but you know, the damaged ones are the ones that floated right to the top and they said, hey, go check these out and tell us what's going on. So at this point, we're going to assume that the ones that weren't reported have performed well, and we can, you know, after a visual inspection, can use those as the good performance dams and match that with the ground shaking. So yes, I'm with you.
Okay, great. We have time for one more. I'm going to call on Assam Abraham. Assam, would you also place your question in the chat? I'm going to unmute you now. You should be able to ask your question.
Thank you, Martin. Thank you, Professor Moss. It's a great presentation with a lot of photos for us to understand what happened. My question is related, a little bit diversion from dams, is related to the electrical power structure. I am talking here about specifically lattice steel tower when I have 4 foundations. If I have you observed anything related to the power structures first, specifically for lattice steel tower? And if it happened that you seen any type of damage for the tower built on the face of the slope or at the ridge, and a little bit about slope stability, if you see any huge damage for the slope stability, especially it was raining before the earthquake. Thank you.
Yeah, great question. You know, when we first go, we cast a broad net, and we were really interested in lifelines. So the Antakya region, which was shaken really hard, so there appears to be both horizontal and vertical ground motions on the order of a G. There was up in the mountains there was a report of that there was some work that was needed on the infrastructure for providing power, but there was no widespread reports of continuous blackouts. And so that was the one blip, and we haven't been able to investigate that, but it sounds like overall the energy infrastructure, the power delivery infrastructure performed quite well. We observed lots of the lattice structures, and they all, and even ones that were crossing the fault, performed very well. And we need to do some further investigations on what equipment needed fixing in the Antakya region. But yeah, I mean, like I said, transportation infrastructure, other lifelines, even with fault crossing, performed pretty well, and that would include the power grid.
Thank you, Professor, for your answer. And it seems like the power line performs very well over there with very high magnitude, like what we heard about. Thank you.
Yeah, thanks, Assam.
Okay, we're now almost at 12:30. If anybody has any more questions, please post them in the chat. Assam, would you post yours as well? I am going to thank Dr. Moss again for an outstanding presentation. Khaled, do you have any last comments?
Yeah, I would thank Professor Moss for this great presentation. And I saw Fake is there. He works for the dam agency in Turkey. So it will be, so he heard that like how interested we are to know about this dam performance. So I'm sure that the data are being collected and it will be useful in future. So I have some observations on this presentation when I looked at the dams. That Sultaniyu Dam is a rock-filled dam, and it performed pretty bad in a sense, even though it was a drought time, and the snow melt hasn't started to come. So whatever fix needs to happen, that needs to happen pretty fast before the snow melt water comes in. So there's some other, like it's not only how it performed during the earthquake, whether we can get from it how quickly we can actually fix those dams, that's important too. And there was another dam that actually failed not right after the earthquake, but after a few days. It was in Syria, so I'm not sure there is any possibility to collect data on that one. So these are just kind of observations, and thank you, Professor Moss, for this great presentation.
Yeah, thanks for the time. And look for our GEER report coming out by April 6th that will have the details that we have collected together to date at that point. So thanks again. Thanks, Marty. Be well.
Thank you, everybody, for participating. Again, Dr. Moss, fantastic presentation. Everybody have a nice day. Thank you.
Okay, ciao.
Thanks, Rob.